Okay, so we ended last time with a partially filled out linked list class definition. We have three member variables and number of nodes, a pointer to the first node, a pointer to the last node, using templates so we can create linked lists of whatever type we like within certain limitations that I won't get into. We have a default constructor. You might like to add a non-default constructor with parameters and say first element, something like this. But I'm not doing that here. Just to point this out, you could write this linked list in a very non-elegant way. You could say first equal new node of type T, and you could set first dot info equal to input, where you prompt the user for the input, enter first node data value, and then read this in, say cn info, the input is going to be of type T, and you could read in that input. I actually don't know if I've done this with templates, arbitrary type, so this could be problematic, especially if this is a string and we have to use getLine instead to allow reading of spaces. Anyways, you could write a constructor for a linked list this way, and you could continue on and say second, declare a second node and a third node. You could prompt the user for the number of in this constructor function. You could pass arguments like the number of nodes, and while counter variable is less than the number of nodes, you do these prompts for the data of interest, and you update. I'm kind of running with this idea. See out enter data for ith node, the ith node counter node number, and you read in the input, and you say for each of those, you say node current equal new node of type T, and for that current node you say current arrow info equal the input value, that whatever the user inputs, and you want to make it a linked list, of course, so you say current, I meant to make that a pointer type, current arrow link equal the previous node, which I haven't declared, but there are ways of doing this, just to allude to that. It maybe it doesn't make sense to do it this way in your opinion, but there are multiple approaches, and this is just the one that I'm taking. So just using the default constructor, and last time we wrote length. The length function is really trivial. The length of the linked list, the number of elements. Maybe you want to call that size instead. I think in the forward list, I think it's called size. The C++'s implementation of a linked list. Yeah, do they have a length method? Do they have a clear method, begin, end, swap? assign clear, empty, and front, get the front. I doubt there will be a back. Like, so we have a member variable named back, um, and we can get the back. So we can potentially write a function to get the back element, or the last element, or the tail of the linked list. Pop front, push front. So notice no references to the back for a doubly linked list, which is called just list in C++, the standard library. There are methods that relate to getting the back element. Anywho, I try to limit my tangents, but this is all good stuff to know about, assuming you go into C++. Okay, so I might call this a utility function. Just, it's nice to have. Every function that we include adds to the overhead of this class. It makes the class occupy more space in memory, of course. So do we want to be minimalist with the number of functions that we include, and possibly make the client program, the main program, have to write more of their own algorithms, and occupy minimal space? Or do we want to take up lots of space, write many functions? There's a limit to how many functions we probably want to define for a particular class, because it perhaps becomes difficult to understand. Too much complexity. Anywho, we wrote an insert first function last time, and I tried to show with a diagram what that was doing. So we created a new node, and then we inserted it at the front of the list. So if we inserted the element 3 first, if we created a node containing the data value 3, it's at the beginning of the list first, at the beginning of our linked list creation. Now, if we call insert first with the value 52 afterwards, then this is going to be at the beginning of our linked list, which we, conventionally we would show this as being on the left. Only I can get this to move. I like this diagram, this diagrams.net website, but sometimes it can be a bit painful. And I moved my bar for some reason. The vertical bar separating the data member variable from the link member variable here. Okay. So we did this, and it seemed like it worked. Let's try one more. Let's insert one more element and make sure that things make sense. We insert -45. I set a breakpoint last time to step through the algorithm, the insert first algorithm, and also the print algorithm. So now I expect to see -45, 52, 3 get printed. Okay, so it seems that, famous last words, but it seems our insert first function and our print functions don't have any bugs, not any obvious ones at least. And maybe it's nice, this is not a big deal, but maybe it's nice to just print with a space here, so we don't confuse this with a stack. This looks more like a list. It's horizontally arranged. You could write a reverse print function. That wouldn't be a terribly complicated thing to do. But as I said, or as I briefly mentioned in the slides, not briefly, but motivation for a linked list, I talk about disadvantages of linked lists. Sorry about the motorcycles, if you could hear that. I didn't mention this in any of the previous videos. It's worth being aware that using the new operator, number one, it leads to memory leaks potentially, which is a problem that C++ was known for. and is still known for. People advocate the use of something called smart pointers rather than new operator, because you don't have to clean up behind yourself with these things called smart pointers. I'll probably almost certainly eventually get into smart pointers in my videos. Um, but it is also slower. So not just memory leaks. And what is this slower than? Uh, Stack memory allocation, which is the usual way that we allocate memory like this. This allocates 4 bytes of memory for an integer type variable named a on the thing called the stack. What is the stack versus the heap? This is good stuff to think about, and eventually I'll look into it further. But yeah, it's the memory allocation is slower. I've actually directly measured this using the Chrono library. It's neat stuff. But I was talking about the insert first function, and it remember I tried to motivate the linked list by talking about how in arrays you have to do something like this. You have to, if you want to insert the element 2 at this position, you have to shift 3 and 4 over to the right by 2 positions, assuming that you want to not overwrite the value 3 here. So you perform 3 operations here. In a linked list, and it's the same with a vector. I haven't dug into the details of how vector writes its insert function. Maybe it does some clever things. It probably does, but for a linked list, theoretically, the advantage is that you don't have to shift elements over. Can we see this with a diagram? Let's say we have first and last, and let's make these things in order so that it's suggestive. Let's say we have the value 2, a node called first, and a node called last. First contains the data 2, and last contains the data 5. So now suppose we create a new node. We create a new node, and its data is the value 4, and we want to insert the node 4 in between the first node and the last node, so that whenever we iterate through this linked list, we have 2, 4, 5. That's the order in which we encounter them. So we want to update this first to point at the new node, and of course, we don't want to cut the last out of the loop, so we want to set new node arrow link to point at last, and then last arrow link contains the value, the null pointer. And again, just to point this out, first doesn't have a box over here saying previous. So what is first, just in case you have some thoughts about that. Okay, so how do we make this happen? And hopefully you can see the potential advantage of this. We didn't have to shift last over to the right. It's more clear with more elements, but we'll see this. We'll see an example in my slides here. So we don't want to just write an insert first function. That is what we did last time. Insert first, and the function definition looked like this. The algorithm for inserting an element first in a linked list looked like that. But let's add an insert after method, and the names here I have to be really careful with this. Void insert after. So we're going to insert some data of type T, and we're going to insert it after a particular node of type T. And what should we call this? The previous, that sounds fine. Previous node in the linked list. Okay. And do we also want to pass by reference? If T is a big object, potentially, do we want to pass by const reference? Potentially, yes. To prevent modification to the data accidentally, especially if we're passing by reference. So what does this look like? I'll try to keep this video not terribly long by sticking with this example. So if we have 1, 2, 4, 5, this kind of begs for 3 to be inserted between these two positions, 2 and 4. So in this case, the node containing the value 2 here is the previous node. So one thing we're definitely going to want to do when we do this is to create a new node containing the value 3. And let me go ahead and write the code for this. 5421 is our current linked list. And let's take a look at that. 5, 4, 2, and 1. Let's make sure it prints correctly. 5, 4, 2, 1. 1, 2, 4, 5. Yeah, I'm just going in reverse. 1, 2, 4, 5. Okay. So we want to write this function, and yeah, one thing we will need to do is obviously create a new node. So node current, or node to insert. Maybe this is a more intuitive name. New node, yeah. Current is maybe current is probably best used for a traversal method. Traverses and then prints the linked list. Current is yeah, new node is probably a better name in this case, and I think yeah, that's what I named that one as well for insert first. New node equal new node of type T. Again, this is heap allocation. Do we have the option of just declaring a node like this? Would this be a better approach? Possibly. I think that's a nice thing to think about. If we were to use that approach, we would have to say new node dot link equal address of some other node. And yeah, this is fine. Maybe the use of the ampersand is not as nice as just saying new node arrow link equal other node. And it's assuming that other node is a pointer type. Okay, I'm just going to stick with use of pointers here. Declare this is a pointer and stack heap memory. Okay, so of course, if we're inserting some data, new node dot info, or rather arrow info, is equal to data to insert. Whatever, so the user, we say, let's just say nums list dot insert after. So it's a good question. What are we going to say here? Node. Do we need to keep track of this node? But for the moment, we're going to insert the value 3. We'll deal with this argument in a minute. The second argument. So let me comment this out. We want to insert the value 3. Again, going back to this picture. not that picture, but in this picture here, we want to insert the value 3. So going back to the function definition, this is a straightforward statement. And if we have a hold of this previous node, we can say previous arrow link equal new node. So what does that do? And does it do it correctly? And is that enough? So let me take a couple of seconds to draw this diagram because I think it's useful. So we have 1, 2. It's useful to see this again. So I'll leave off the links 1. Oops. We'll leave off the text link. Okay. So 1 is linked to the node containing the value 2. And then 2 is linked to the node containing the value 4. And 4 is linked to the node containing value 5. And 5 is linked to the null pointer, the end of the list. That is the last node. So this is last, this is first, and we have just with this code, previous arrow link. Let's go ahead and make a box that says previous. Previous node. This is the new node. We have just said previous arrow link previously pointed at this node, but now we have updated it to point here. You get the point. Previous arrow link equal new node. I think that works without any problem. And we want to say new node arrow link equal. And that's a good question. The order of operations here, the order of updates to the link values. New node arrow link equal what? We want to not cut these guys out of the loop, but I just have with this statement. So new node arrow link equal. And if you think about it, if we have a hold of previous and before we perform this statement, previous arrow link pointed at this next element in the link list. So previous arrow, new node arrow link equal previous arrow link. Okay, I think this, so what that has done, what that will do is this. And now setting previous arrow link equal to new node after that, we'll do this. And we could scooch things over now. And scooch this up. Maybe. I'm just rearranging things to make it look a little more pleasant, hopefully. And we not lost the null pointer here, so let's not lose that. Probably get the point, but okay. So I think this works with that. I think this algorithm makes sense. Let's take a look at the code here. New node equal new node of type T. Info is the inserted value. new node arrow link equal previous arrow link. Okay, previous arrow link equal new node. Okay. First three lines of code result in this diagram. And the last line of code does that update. Okay. Okay, I mentioned memory leaks there. Okay, so let's write. In order to get this to work, we will need a get node function if we want to write the insert after function in this way. We are expecting a node here as the previous node. So how do we do that? We haven't, yeah, how do we do that? What is this going to be? It makes sense to write a get node with value function. So this is essentially a search function, and we're going to iterate. We're going to use the current node and loop through until we encounter. I did this in an interesting way. I guess we'll write a search function later, like search for a particular value. Yeah, it's more complicated. Node position. Let's just go with it. So by node position, I think this is usually not done in linked lists, referring to indices of nodes, but it makes some sense. I think I took this out of a textbook, so I'm not just doing something strange. Excuse me, this value should be 3. Sorry if that was confusing. Again, hopefully the slides are carefully made and weren't just typed on the fly like I'm doing right now. So we would like to say insert after the second node in this case. 1, 2, second node. We want to be able to say node, second node, something like this, equal get node, or nums list dot get node at the either the first index, number 1 or 2. It depends on whether we start the counting at 1 or 2, at 0 or 1. So okay, we would like to be able to say this. Integer node position. Okay, So if we specify a position, this is not going to be a terribly difficult function to write. The get node function, it's similar to the uh, print function. We're going to start at the beginning of the list. Now we set up a current node, a temporary node, an iterator, set it to first but instead of saying while current is not equal to null pointer, we advance until we get to the node position. So we say while wanted to stick with my approach in the slides. Yeah, I set up a loop counter variable int I equals 0 and incremented int I equals 0 while I is less than node position, the node index. We increment I and we step along the chain. We say current equal current arrow link. And we'll have to be careful we don't step one position too far here. But once we have become equal to the node position, we return current here. So let's just test this before we do the insert after function and say cout. So what is the node at the 2 position? Is it 1? Is it 2 or is it 4? Yeah, let's just see. What's the data value? So what's the info contained in this node? And let's hold off on the print. So is this a second node or the third node? Do I need to change this to a 1? So we printed 4. So that is 1 to 4. So that's the third node. So let's say 1. Okay. And that gets us the value 2. Okay. And hopefully it's not unpleasant to change on the fly here, but let's say insert 5. So A, B, and not C, but D, and then E, and we want to insert the value C. And change this to a character type. Okay, so now node 1 should be B. The info contained, okay, is B. And how about 0, A, and let's go out of bounds, 10, get node 10. And how will this be handled? An exception gets thrown because we step to the null pointer. An intentional error. Okay, so, all right, so second node, let's change this to the appropriate value, which is 1. That's, now we want to insert after the second node. Just one more time, let's verify that that's B. That's where we want to insert that. Okay, B. All right, and now we call insert after second node, we insert the value C, and we want to see A, B, C, D, E, A, B, C, D, E. Let's see if we do A, B, C, D, E, and we printed that B on the other line because I didn't comment that out. Okay, so that's an insert after function. That is, in a way, that's a nice stopping point. Yeah, we definitely won't get into the search function in this video because that is a fairly, that's not the terribly complicated function. The most complicated linked list function that I write is delete node with info, which is, yeah, it's the most complicated function, so it'll probably have a video of its own, as you can see. Logic's not terribly complicated, but yeah, the body of the else continues in a few slides, so Yeah, it's got a while loop. Yeah, it's pretty complicated in a good way. Okay, but we finished get node. This is a test that I do in the slides. There's one last thing that might be nice to do is let's say linked list length equal nums list dot get dot length, and we could say last node equal nums list dot get node at linked list length. And do we have to subtract one? Let's just see. So now let's print last node arrow info. And we'll hold off on the print, and we'll hold off on the insert after. We expect to see AB, ABDE, so we expect to see E, or yeah, so we see E. If we go one too far, we'll step out of bounds and hit the null pointer, get that exception thrown, a read access violation. Okay, so let's not forget to subtract one here. Now, can we insert after the last node? Well, this is kind of an edge case. It's good to verify that we can do this. So can we insert the value F afterwards, after E, and will we print A, B, D, E, F? Let's see if this works. There are potential problems in these edge cases. So no exception was thrown, so that's promising. A, B, F, D, E. I have to update my code properly. A, B, D, E, F. Okay. Now let's say first node and make sure we can insert. So this is called insert after. It's not insert before. So I think an insert before function would not be terribly difficult to write. And possibly famous last words there. Let's insert after first node the value, what comes before A in the alphabet. That's just being silly there. First node. Insert after first node. The value F is, it's fine. I'm not gonna, well, I guess we could be kind of cute and say uppercase Z comes before, in the ASCII ordering system, uppercase characters come before lowercase characters. So this should print capital Z, as the British say, A, B, D, E, and a Z before it, assuming that there are no bugs in this edge case. Edge case is what I'm saying. So A, Z, all right, it's an insert after. So anyways, my mistake. We didn't write an insert before function A, Z, B, D, E, so that makes sense. I mean, this does not make sense, but the code is working in the way we expect it to. Okay, so that's a fairly painless demonstration of how we would write a couple of functions for a linked list, a get node list, get node function, and an insert after function. Not the optimal approach for sure. It's not anything comparable to the standard forward list in C++, but we're just playing around and learning some things. So that's it for this video, and in the next one we'll talk about the search function, and we'll see how it goes.